Now, the kinetic molecular theory is really helpful to chemists. It does a lot of things, and there are some assumptions that are made in the kinetic molecular theory that we should talk about. And one of the assumptions is that gases are just constantly moving around. It's random, there's no way to predict it, and that's a pretty good assumption. All right, at 0 Kelvin, absolute zero, that's when the gases would stop if you still had a gas, but up until that point, there's always going to be some movement. Pressure, the concept of pressure, arises from the idea that collisions with container walls by the gases create this kind of force. And that's kind of cool. So the idea of pressure, like where pressure comes from, it's all the little molecules smashing into the container walls, and it creates like a type of a force. And that seems to work out pretty well. Now, the kinetic molecular theory also predicts that there are no attractive or repulsion forces between the gas molecules. And when molecules collide, it's elastic, like you don't lose any energy to things like friction, stuff like this. Now, this is an okay assumption. It's not perfect. And in a future chapter, we'll talk about intermolecular forces. Intermolecular forces are truthfully a little bit present when it comes to gases, but most of the time we can ignore them. But just realize that this third one here, I'm on a little shakier ground than I am the first two, which are considered pretty good. And then finally, the volume of molecules is negligible, i.e. almost zero. And that works really well as long as you don't get down to 0 Kelvin. Then you start to have some problems. So the KMT is cool. There's a lot of neat things about the KMT. The assumptions, some of them are better than others, but we'll talk about this as we go through the course.
Gas molecules are in constant motion and frequently collide with one another. Although not all the molecules in a gas sample move at the same speed, the higher the temperature of the gas, the greater the average speed and kinetic energy of the molecules overall. This higher level of energy allows molecules to disperse more readily, which is one reason we smell aromas better when temperatures are higher.
Now, in the last slide where we talked about the assumptions of the kinetic molecular theory, we assume that those molecules, which have a mass, they're in motion, all right? Now, mass molecules that are in motion, motion is a speed or velocity, and speed is usually measured in meters per second, so just FYI about that. And for this discussion, our mass, m, it's going to be in units of kilograms per mole. And I'll talk about why that is a little bit. So if they have mass and they have motion from physics, we can actually calculate their energy. Now, energy is something we're going to talk about more in the next chapter, but the kinetic energy is the energy of movement, and it's usually covered in and kinetic energy is usually measured in a unit called joules, and we'll talk about that here in a little bit. So anyway, when you're talking about this then, the kinetic energy of a molecule of gas equals 1/2 mv squared. And this is an expression that comes from physics. And we're not going to measure kinetic energy, but I want you to know about this because the things we're going to talk about are going to be really relevant. Now, in addition to that, the kinetic energy of any gas sample is equal to 3/2 RT. And this R value is the energy R, which again, you don't really need to worry about that. So why am I sharing all these weird expressions with you? I understand. So first of all, let's look at the videos on the right. The higher temperature gases were moving a lot faster. All right. They have a much faster speed, much faster V, which is the speed in meters per second, than the low temperature gases do. Okay. So as temperature goes up, the kinetic energy of the system, the energy goes up. And if it's the same gas, then the speed will go up as well, which is cool. So that's one thing I want you to realize. At the same temperature, all gases will have the same kinetic energy, all right? Doesn't matter if it's CO2 or water or helium, stuff like that. They're all going to have the same energy. If it's the same gas, like you're just talking about water or you're just talking about CO2, then the speed will change. The mass is a constant and the speed will change. However, if the same temperature, all the gases have the same kinetic energy, and you are comparing different gases, for example, CO2 and hydrogen, well, CO2 is a much bigger molar mass than hydrogen. So if the mass is bigger, the speed is going to go down. So we're going to see that the mass of the gas affects the speed. If you have a set amount of energy, which is dictated by temperature, then kinetic energy is proportional to the mass and the speed v of the gas. So what that means is that heavy gases will go slow and lighter, smaller gases will go faster. And we'll talk about this here in a little bit. So we're not going to calculate kinetic energy in this class. That's not something we're going to do. But we can use these expressions to understand, first of all, that at the same temperature, all gases, doesn't matter what they are, all gases have the same energy. Temperature goes up, the energy goes up, temperature goes down, kinetic energy goes down. However, if you have two gases that are at the same temperature, one of them will be faster than other. Mass times speed velocity, mass times velocity squared is proportional to the kinetic energy. So if you have a heavier molar mass, a bigger m, you're going to have a smaller v. Heavier masses go slower. On the other hand, you have a light, small molar mass, m, you're going to have a bigger v velocity. Smaller molar mass gases will go faster than heavier molar mass gases. Let's kind of review there a little bit. At the same temperature, all gases will have the same average energy, and it doesn't matter what the gas is and stuff like that. However, different gases at the same temperature will have different speeds. They'll have the same overall energy, but they will have different speeds. So we saw that the energy is proportional to temperature. That's why all gases have the same energy. However, energy is also proportional to the mass and the speed v of the gas. And if you have a bigger gas mass, it's going to have a smaller speed. And if you have a smaller molar mass gas, it's going to have a faster speed. So Maxwell came out with this crazy expression. Notice that it's the square root of something squared, which is kind of crazy. It's called the root mean square speed. You don't need to worry about it. We're not even going to calculate it. But what I do want you to see is that u is the speed, and it's proportional to temperature in the top and molar mass in the bottom. So as the speed, if you want the speed of your gas to be bigger, you want to have small molar masses and bigger temperatures. On the other hand, smaller temperatures will have smaller speeds, bigger temperatures will have bigger speeds. And if you're comparing two gases with different molar masses, the smaller m molar mass gas will have a bigger speed, and the bigger molar mass m gas will have a smaller speed. So it's kind of cool. So if you imagine, for example, big xenon and small helium, all right, and you're at the same temperature, big xenon is going to be slower, and small helium will be faster. That's kind of the idea going on here. So if you're thinking about diffusion and effusion, the helium will diffuse and effuse much faster than the big xenon will. That's where all these things kind of come into play.
Cars on highways travel at a variety of speeds. To show the distribution of automobile speeds, we could plot the number of cars moving versus their velocities. Molecules in the gas phase show the same variability of speed. Plots of molecular speed distributions are called Boltzmann plots.
If you've driven on the freeway, you'll definitely notice that people have different speeds on the freeway, all right? And I like to think of myself as somewhat average. I go, probably 5 miles over the speed limit. Okay, Smokey's going to give me a ticket now. But anyway, hopefully that's somewhat normal for a speed. And then you've got some people that, oh my gosh, they think they're in the Indy 500. They just go crazy speeds on the freeway. And they always make me really nervous. But anyway, then there's also, though, the drivers that I swear they just got out of their senior citizen home or something, and they drive super slow, and it drives me crazy. But on the freeway, there's usually an average speed, which is, 65 miles per hour, if that's the speed limit, give or take a little bit. And so there's going to be cars that go a lot faster. There's going to be cars that go a lot slower, but the average speed is about, say, 65 miles per hour. Well, gases and their speeds have something similar. And And gases always have an average speed, which is the height, the top part of that curve right there. All right. So most gases will go that speed. Let's say it's 500 meters per second. Looks about right. Then there will be, though, some gases that are like the senior citizens, and they'll go at speeds that are much smaller than that. On the other hand, there's going to be those speed racers that go with speeds that are much faster, the ones over here. Most gases have an average speed of about halfway up there, about 500 or so meters per second, and they're good to go. And that's what Maxwell was referring to when he did the square root of the speed squared thing. It's the average speed squared and then squared root. Now, on the right-hand side, the top graph, you have two different temperatures, okay? 25 and 1,000 Celsius for O2. And the blue line right there is for the lower temperature. And most oxygen travels at that speed. We'll say it's for 50 meters per second. That's the average speed for oxygen at 25. But when you increase the temperature, then the average speed is about right there. It's closer to 800 meters per second. So temperature goes up, the speed goes up. But technically, that's the average speed, because even at the colder temperatures, you're going to have some speed racers over there on the far right part of the graph, and they're going to go faster than the average speed, even at 1,000. And at both temperatures, even the hot temperature, you're going to have some molecules over here that are the senior citizens driving super, super slow, all right? This is the idea. Gases have a range of speeds, so we can talk about the average speed, but there will be exceptions, both low and high for both of them. The lower right-hand graph is the effect of molar mass. Now, O2 is about 32 grams per mole. That's the biggest molar mass. And N2 is about 28 grams per mole. Water is about 18 grams per mole. And little helium is about 4 grams per mole. So smaller molar mass means faster speed. But again, technically, it's the average. Helium's average would be right about there, and oxygen, which is bigger here, would have an average up there. But some of the oxygens down here are going close to the average speed of helium, all right? And some of the helium, which is super fast, it has its own senior citizens down there on the left-hand side that are going much slower than the average speed of oxygen. So when we're doing all these calculations and discussions, how speed goes up as molar mass goes down, et cetera, we're talking about averages, all right? And there will be statistical distributions, Boltzmann plots, these kind of things that talk about a better way to describe the speeds. But in the average version, molar mass goes up, speed goes down, temperature goes up, speed goes up, but it is an average, and you'll see exceptions on both sides. This is the kind of question you might see. This is our diborane example again. Diborane is burning in oxygen. It makes boric acid a solid and water. And there are 3 gases in this reaction. Let's put them in order of increasing velocity. So speeds increase as molar mass decreases. So what that means here, the slowest gas will have the biggest molar mass, and the fastest gas will have the smallest molar mass. So in this problem, what we want to do is we want to figure out the molar masses of our 3 gases, B2H6, B2O3, and H2O. Now, boron is roughly 11 grams per mole. So 2 borons would be 22 grams per mole, plus 6 for hydrogen. This is going to be about 28 grams per mole. This is really bad sig figs, all right, but hopefully you get the idea here what's going on. Oxygen is about 32 grams per mole. So that's a little bit bigger than B2H6. That means it's going to be slower. And water is about 18 grams per mole when you figure it out. So that's the smallest molar mass. We would expect it to go fastest. So if we want this in order of increasing velocity, we'll put the oxygen first because it's the biggest molar mass. We'll then put B2H6 because it is a little bit lighter than O2. It'll go a little bit faster. And water should be the fastest of all. It has the smallest molar mass. So we're going from heaviest molar mass to smallest molar mass. That's the order of which these things go on. We're not going to put the B2O3 in there because it's a solid. All right, it doesn't have speeds and stuff like that in this context anyway. So use the molar mass to figure out a lot of these problems. And by default, smaller molar mass equals faster, bigger molar mass equals slower. Now, ideal gas law and all these things we've talked about is great almost all the time, but there are some times when the ideal gas law doesn't work as well. And these things happen if you're, say, working in industry. It's more likely to be something that you'll think about than if you're working, say, here at Mount Hood Community College. But generally speaking, because real molecules have volume, that tends to mess with the ideal gas law. And volume, the V term in PV equals nRT, may not be adequate to describe how gases actually work. Also, there are intermolecular forces at play. Intermolecular forces are something we'll talk about in a future chapter, but it's basically the way that the molecules stick together a little bit. Without intermolecular forces, gases would never become liquids or solids for that matter. So intermolecular forces are definitely important, and they do start playing a factor as you get to the right temperatures. So generally, scientists feel that high pressure and low temperature conditions are the places where the ideal gas law breaks down more often than not. And high pressure is relative as well as low temperature. Most of the time in my world, ideal gas law has worked great. But if you're working in an industrial place where you have huge tanks of hydrogen or carbon dioxide that you're using or something like that, you may want to think about high pressure and low temperature conditions and see if the ideal gas law perhaps isn't behaving as well as it might. The main equation that's used to make the ideal gas law work a little bit better is called the van der Waals equation. And there are several equations like this that are out there, but van der Waals seems to be used most often than not. And in the van der Waals equation, you can have a pressure little term that's a little bit different and a volume term, and all of that equals nRT. And so most of the time, if the ideal gas law does break down, the van der Waals equation actually will help you out. So notice that in this equation, it was initially PV equals nRT. But what van der Waals did is he added a term to the pressure amount there, and he subtracted a term from the volume. Now, N is just the moles, V is the volume, okay, and A and B are constants that have to do with the gas itself. A lot of times people have better results when they use the van der Waals equation than if they use the regular ideal gas law equation. And it seems to work best, again, if you have low temperature and high pressure conditions. That's when you may want to think about using the van der Waals equation. Here's an example of some A and B values, which just come from a textbook, and these are certainly nothing you'd ever have to memorize. For chlorine gas, A is 6.49, and B is this 0.0562. So if you had 8 liters of chlorine in a 4-liter tank at 25 degrees Celsius and you use the ideal gas law, the ideal pressure that you would calculate, 49.3 atmospheres. But when you use the van der Waals equation, it comes out to be 29.5 atmospheres of pressure. So quite a difference in the expected pressure. Apparently in these conditions, the van der Waals equation works better than the ideal gas law.